Unit 3. The derivative. Lecture 3.1. The derivative. Okay, the derivative deals with instantaneous rates of change, which is important. Okay, we've seen it before and we'll see it a lot. And you see it a lot in science. And it's a special kind of limit, which is part of the reason why we talk about limits so much. What are we going to talk about? We're going to talk about instantaneous velocity, instantaneous rates of change. We're going to talk about the derivative at a point and the derivative as a function. We're going to talk about notation. We're going to talk about graphs of the derivative and the function. We're going to talk about differentiability, and then we're going to talk about higher order derivatives. Not all in the next 5 minutes. This hopefully is the last time you have to see these two idiots. Okay. For hopefully the final time. Instantaneous velocity. Okay, remember this guy dropped that rock on that other guy. Okay, so what do we want? We want to know how fast that ball is going 3 seconds into its fall. Okay, we wanted to know the instantaneous velocity at time equals 3. So what did we do? We determined the average velocity, or the slope of the secant, okay, from 3 to 3 plus delta t. Okay? Okay, so we got the average velocity, again, as the slope of the secant from 3 to 3 plus delta t, as the displacement over the time elapsed. Okay? Those, you have all of those already, okay? Those are either in slides or in your notes somewhere. So I just rewrote them for you and color-coded, but you have all of those. Okay, and to get the instantaneous velocity, what did we do? We shrunk the interval down. We brought that point in toward the point of interest, and then the secant gets closer and closer to the tangent. The slope of the secant gets closer and closer to the slope of the tangent, and the average velocity approaches the instantaneous velocity, okay? So the instantaneous velocity is just the limit, as delta t shrinks down to 0, of the average velocity, okay? And we do that using what we already talked about, okay? And I showed you an alternative approach, very, very similar. Instead of talking about 3 plus delta t, your other time, you can call it t star, and you bring t star in toward 3, okay? And that's it.
So essentially, instantaneous is the limit of the average velocity.
Yep.
Okay.
Okay? All right. Any questions about either of those two? Okay, either you shrink delta t down or you bring t star in toward 3. Okay. Okay, let's write out a general approach. To find the instantaneous velocity at a particular time t equals a instead of 3. So I'll do the same stuff, except instead of writing 3, I'll write a over and over again. Okay. All right. So let's talk about the average velocity, which will be a function of the time interval. I'll do approach 1 for now. Okay. So the average velocity on the time interval between a and a plus delta t. Okay. Well, the average velocity on the time interval between a and a plus delta t. Okay, so that's just displacement over elapsed time. Okay, p is the position function. Okay, over there it was called y. Whatever. Okay? Okay, displacement over elapsed time. And what's this? It's the slope of those secants. Okay. And you'll remember this kind of thing is going to have a removable discontinuity at 0. Okay, from that we get the instantaneous velocity is equal to the limit as delta t shrinks down to 0 of that guy, of the average velocity. Just as before. Literally what we did before, except it's a instead of 3. Okay? Okay, again, position on some straight line. P is the position function, the function of time. Top is displacement, the bottom is time elapsed. This thing is called the difference quotient. Difference quotient. Because it's a quotient of two differences. Okay, and again, this guy had a removable discontinuity at 0. When we take the limit, we're essentially filling in that hole like we did before. And that's all we're doing. We get the instantaneous velocity by shrinking the interval down. Okay? That was the slope of the secant, or the slope of the secants, and that is the slope of the tangent. Okay? Okay. I will write very quickly the result in version 2, and that's the last thing I'll write. Okay, version 2 with the T star thing. Looks like this. The instantaneous velocity is the limit as T star goes down to the time of interest of, again, the change in position over the change in time. Okay? And that's it. We'll do the rest of the derivative tomorrow. Or next class. Thank you. Okay, we started the derivative. And we talked about those guys again. And this is our first foray into differential calculus, right? We talked about two branches of calculus. This is one of them, differential calculus. Okay, discovered in the late 1600s, revolutionized everything. Okay? This couldn't be more important. We talked about calculating instantaneous velocity from position as a function of time. Twice, in two different ways, slightly different ways. And that's where we stopped. So let's carry on from there. All right. I'm not making money off of this. Here we go. The derivative at a number. I'm going to say number. If you change that to point, that's perfectly fine. Okay, so this is the general version of what we did last time, right? So we talked about instantaneous velocity last time. Let's just talk about instantaneous rates of change in general. Okay, the instantaneous rate of change of a function f at a number a is equal to the slope of the tangent to the graph of f at x equals a. Okay, just like what we did before, just more general. Instead of saying position now, I'm saying f. Okay? And we have two forms of that. So we could write this, the limit as h approaches 0, used to call it delta t, as h approaches 0 of f at a plus h minus f at a all over h. Okay? Or equivalently, the limit as x approaches a, I used to call that x star or t star or something like that. F at x minus f at a over x minus a. Okay? Just what we talked about, only I'm calling it f instead of position. And some of the t's changed to x's and so on. Okay? Okay. This guy and this guy are called difference quotients. I wrote that word last time. They're called difference quotients because they're a quotient of differences, more obviously here. If you need any evidence that these two forms are equivalent, let me know. Simple substitution will do it. And what can we say? What is a difference quotient? It's an average rate of change, okay? This thing is an instantaneous rate of change. The difference quotient is an average rate of change. Okay, in this case, over the interval from a to a plus h. In this case, over the interval from a to x. Okay, average rates of change. As you take the limit, you get the instantaneous rate of change. So again, these are difference quotients. They're average rates of change. Of f with respect to x. Okay. And at long last, we call this guy the derivative of the function f at the number a. Denoted f prime, which looks a bit like an apostrophe, a. The derivative of a function at a number, or a point if you prefer, the derivative of a function at a number a is f prime at a equals the expressions I just wrote, if this limit exists. Note that I didn't write plus or minus after the 0 or the a, so typically we're talking about the two-sided limit. Also, when I say this limit exists, I do mean that limit. I mean the limit of the difference quotient. I do not mean the limit of f at a, okay? This is not the limit of f at a. This is a very different thing. Okay. Any questions? Example time. Example. F at x equals, I will write slightly lower because the lights are annoying. F at x equals square root x. And you want to find f prime at 2 and f prime at 5. Okay? All right, so what we could do is we could just apply that definition at 2 and then again at 5 and do it that way. Or, to save us the trouble of doing the whole thing over from scratch again, we can just do it at a general a. So let's do that. To save trouble, let's do the work for some general a. For any a greater than 0, let's do this. F prime at a is equal to, let's use the first definition. The limit as h approaches 0 of f at a plus h minus f at a all over h. And just plug in. It's the square root function we're talking about. The square root of a plus h minus the square root of a all over h. You're experts now. You know what to do. Yeah? You multiply by the conjugate radical top and bottom. You wind up with an h that you can cancel out. So I will skip those steps now. And if you need help, let me know. And after that, you wind up with this. A plus h plus. There we go. Again, multiply by the conjugate radical top and bottom. Simplify, cancel, and you get that. Okay. Note, the thing I'm taking the limit with respect to is h, okay? Not a. Okay? Treat a as a sort of fixed parameter, okay? A fixed number, okay? In this situation. It's h that's moving around in the limit, okay? So anyway, you can use continuity of this thing with respect to h, or you can use limit laws, and quite straightforwardly, you will wind up with 1 over root a plus 0 plus root a, and that's just 1 over 2 times root a. Okay? H acts as a variable, a acts as a fixed constant. Okay? All right. The question asked you for f prime at 2 and f prime at 5. So now we just plug into that thing. F prime at 2 is equal to 1 over 2 root 2. F prime at 5 is equal to 1 over 2 root 5. And in case anyone was wondering why we cared so much about that method of doing limits, this is why. Okay. Any questions at any time, let me know. That's not part of the no talking. There you go. Tangents drawn at x equals 2 and x equals 5. And if you trust me, they were drawn with those two slopes. Okay? And they do indeed look like the tangent at those 2 points. Okay. I'll talk about this later. I said a greater than 0 for a reason. If I did a less than 0, this thing wouldn't have existed at all. If I said a equal to 0, I would have had another problem that I'll discuss in a bit. Okay. If I told you that f, this is still part of the example, sort of, if f was the height of, because we love trees so much, the height of a tree in meters, as a function of, stupidly we'll still call it x, as a function of time in years, okay? And you calculated f prime at a. What does f prime at a mean? It's how fast is the height of this thing growing at time a? Okay? Is that clear enough? Okay, how fast is this guy growing at time a? And what are the units of that? The same as the units of the difference quotient. Okay? M over y, meters per year, which is perfectly sensible. Okay? Okay. It's an instantaneous rate of change. All right, what did we do? We got an expression for f prime at a, and then we plugged in values for a. That looks a lot like a function, okay? So instead of talking about this thing as the derivative at a number, we could talk about the derivative as a function, okay? So instead of talking about, a, let's talk about an independent variable x, or t, or something like that. Okay. Here we go. Almost nothing has changed. Again, instead of treating a as a fixed number or constant, we deal with x or t or something like that, which is an independent variable. Okay? And now we can talk about the derivative as a function, which is pretty much what we were doing there anyway. Given a function f, the derivative of f is the function f prime defined by that, again, limit of a difference quotient. The domain of f prime is the set of all x values for which this limit, again, not the limit of f, that limit exists. Okay. Okay, and if you're interested in the derivative at a particular number, what do? You either use the definition of the derivative of the function at a point, or you use that guy and you plug in that value. Okay? So if you want f prime at a, you either use the last definition, or you find this thing and you plug x equals a in. Okay. As before, when you're taking the limit, it's x that's moving around, it's h that's moving around. You treat x as fixed when you take this limit. Okay, h moves around, as it did there. And finally, note that a function has a lot more information in it than just the derivative at a point, okay? So when we get f prime at x and treat it as a function, we're talking about what goes on everywhere. We're talking about a lot more information than just the derivative, the instantaneous rate of change at a single point. Any questions about this? Okay, so derivative as function. For example, over there, we had f at x equals square root x. F prime at x is 1 over 2 root x. Okay? Just x instead of a. And again, there's nothing special about x. It could have been called t or something. Okay. What does the domain of this thing look like it is? Positive. Okay. Good. The square root tells you non-negative. The division tells you non-zero, so you wind up with positive. Good. So the domain of f prime is the positive reals. Okay, and that is right. Okay, so that the exclusion of all the negatives is right because the difference quotient just isn't defined there, and the exclusion of 0 is right. Why? Two reasons. One, which is not important really, is that the two-sided limit doesn't exist at 0. The more important reason is a vertical tangent problem, which we'll come across again. Okay, I will mention this again. But anyway, we exclude 0. F prime does not exist, that limit does not exist at 0. Okay? If that's confusing, stay tuned, and if it's still confusing, let me know. Okay. Get a question raised?
You did it with the power rule.
Ooh, what's this? What?
You did it with the power rule.
I don't know what power rule is.
Sorry.
First principles.
Sure.
Okay? Does not confuse. Okay. Rotation time. There's a sickeningly large number of ways to denote the derivative. Okay, if we write y equals f at x, x being the independent variable, y being the dependent variable, f being the function, we can write this. We can denote the derivative function of f as, here we go, y prime, f prime at x, dy over dx, df over dx, d over dx, f at x, 3 more, big D, f at x, big D sub x, f at x, and y dot. That's it. Okay. I'm sure there are others. And in fact, I know there are others. Okay? Some will use more than others. I really doubt we'll use this or this. Okay. Who's responsible for this stuff? Lagrange. And I hear Newton had something to do with this as well. Leibniz. It's like biology now, huh? You have to memorize names. You don't have to know them. Our friend Euler. And this is called Newton notation. Especially when you're differentiating with respect to time. Okay? And there was a fight involving that guy and that guy about who invented calculus first in the late 1600s. Okay? All right. Okay, comments. Differentiation. Is the process of determining the derivative okay? It's an operation that takes a function as input. Normally we talk about taking a number as input. Now we're talking about taking a function as input. And produces another function called the derivative as output. Okay, so it's a special kind of machine. Okay, and where do we represent this? In notations like d over dx, f at x, and big D, f at x. That's how we're talking about it. We're saying do this to f, do this to f. Okay, these are called differentiation operators. Differentiation operators. Okay? All right. What else? Something like dy over dx. Okay, which is Leibniz's notation. He's very, very suggestive. The limit as delta x goes to 0 of delta y over delta x. That's essentially that, okay? What's the change in y over the change in x, and then shrink down the interval over which you compute it? That's what the derivative is, okay? Really, really suggestive. dy over dx is the limit of delta y over delta x. Change in y over change in x, okay? But do not treat this as a ratio yet, okay? Leibniz treated it as a ratio, and he did well, okay? And he was vindicated later, despite the fact that he was being very sketchy when he did it, okay? But for now, this is not a ratio. It's just one big symbol. It's in one big piece, okay? Later on, we'll talk about something special. Okay? Yes, ma'am?
I don't really entirely understand what you mean by if an operation that takes f as an input but produces...
We do differentiation to f, and we get f prime out. So if I have a machine that's a differentiation machine and I feed f to it, it spits out f prime.
Okay.
That's it.
I didn't
just
see
an
that
idea.
prime, sorry.
Which one?
Yeah, it says produces f, but it says f.
F prime, yeah. Yeah, I tried to bold it, but it doesn't really work. Okay? All right. Okay, and the last point on this, to show the derivative at a number a, in Leibniz notation, you write, I want to write y, yeah, dy over dx at x equals a, dy over dx at x equals a, something like that. Okay? So that's the same as writing something like f prime at a. Okay? Are there questions? Okay. Ooh, hello.
Would we ever be required to write in one specific notation?
I doubt it. I doubt it. You should understand them all. So if we write dy over dx, now go, what is this? Yeah. Cool? Alrighty. Okay. Please tell me if there's questions. Graphs. F prime is a function, so we can graph it. At each x value, the y value in the graph of f prime is the slope of the tangent to the graph of f at that x value. Okay? What we talked about before? Nothing new. Good? Okay, we're saying f prime is equal to the slope of the tangent to f. That's it. Okay. And you might hear someone say the slope of f instead of the slope of the tangent at f, because if you zoom in close enough on something that's well behaved, it'll look like it's tangent if you zoom in close enough. Okay. So note in particular, f prime being positive, negative, or 0. I suspect many of you already know what I'm talking about. Okay? Where f prime is 0, okay, the tangent to f had better have a slope of 0. It'll be horizontal. Okay? So where f prime is 0, f is flat at an instant. Where f prime is positive, the slope of the tangent to f had better be positive. Okay? And some of you will recognize that as a symptom that f is increasing. If f prime is negative, then the slope of the tangent to f will be negative, which is a symptom that f is decreasing. Okay, so watch the signs of f prime. Also look at the size of f prime. If f prime is big, here, then f is steep. If f prime is small, here, f is shallow. Okay? All perfectly logical. So whenever I put up a graph, do some basic checks. Okay? Because as you know, I like graphs. Questions? Differentiability. Okay, a function f is differentiable at a if f prime a exists. A function f is differentiable on an open interval I if it is differentiable at every number in the interval. As you expect, if you can differentiate, it's differentiable. No surprises at all. Example. Where is the absolute value function differentiable? All my sleazy abbreviations, please forgive them. You'll remember I asked you a few days ago, where is the absolute value function continuous? I asked you that so you wouldn't confuse it with this. That's what that looks like. Y equals absolute value of x. So what are we asking? At what points has this guy got a well-defined tangent slope? Okay? Okay. Is it obvious where the problem is?
Yeah.
There's only one special point, right? Okay. All right, here we go. Let's do all the others. 4. X less than 0. I will be skipping steps here. Okay. For x less than 0, what's the derivative? By definition, okay. Okay. Okay, if x is less than 0, then absolute value of x is just negative x. Absolute value of x plus h for sufficiently small h is minus x plus h. So, lim, that's an L, minus x plus h minus x. What happens? Minus x plus x, ding ding. We get h over h. The h's cancel, and we wind up with 1. The limit as h approaches 0 of 1 is 1. If you can't do any of those steps, let me know. Okay, that seems pretty sensible. To the left, you draw tangents. They're all going to have, whoa. Ah! See, this is skipping steps, huh? Okay, here we go again. Minus x plus x, cancel, cancel. You wind up with minus h over h. The h's cancel, you wind up with minus 1. The limit as h approaches 0 of minus 1 is minus 1. I apologize. Okay, any tangent you draw to the left here is going to have slope minus 1. Okay.
Wait, so for this, since it's like absolute, that means we need to kind of do it twice?
Yeah.
Okay.
Yeah, if you're going to do it first principles, yeah, you have to do it twice. Okay? For x greater than 0, does that make sense? Okay. All right. Okay, so for x greater than 0, you do the same sort of stuff, except you're on the other side. So this is x plus h, and that's just x. And then I get the thing that I wanted to say, which is plus 1. Okay? And if you draw any tangent on this side, yeah, it's all going to have slope plus 1. So it all makes sense. Okay. Now what happens at evil 0? Okay. The derivative at 0, again, first principles. Psh, sloppy today. Okay? All right. What's this guy equal to? Absolute value of 0 plus h minus the absolute value of 0 all over h. That's just the absolute value of h minus 0, so who cares, over h. Does that make sense? Okay, we did all this, now we have to see what goes on at 0. Okay. We want this limit. We have a problem. This guy's piecewise defined, and we're talking about what goes on at the transition, so we have to do two cases. So, the limit as h approaches 0 from the left of that difference quotient. Okay, when h has a negative value, the absolute value of h is negative h. Negative h over h, cancel, negative 1. The limit as anything happens of negative 1 is negative 1. Okay? What does that mean? That means if I look at 0 and I look at the immediate past, that suggests a tangent with slope minus 1. And if you like, don't worry about this, if you like, you can call this the left-hand derivative. At 0. Don't worry about it, okay? Just for the record, it makes sense to call that the left-hand derivative. Okay, and on the other side, for h having positive values, absolute value of h is just h, the h's cancel, you get plus 1, the limit of plus 1 is just plus 1. And that's called the right-hand derivative at 0. Hey look, the one-sided limits disagree, so the limit doesn't exist. So the two-sided limit doesn't exist. So f prime 0 does not exist. Okay? Again, what does that second guy say? It says that if I look at the present value and the immediate future, that suggests a tangent with a slope of plus 1. Okay? So if I look at now and the past, or now and the future, they suggest different tangents, which is bad. You're not differentiable. Okay. So, f prime at x is minus 1 for x less than 0. F prime at x is plus 1 for x greater than 0, and that's it. So the domain of f prime is everything but 0. F is differentiable everywhere but 0. Okay? Questions? Mistakes I made? I'm going to start doing that thing where I claim if I do make a mistake that I planted it. No question. Oh, hello.
Is it necessary to show the last step if you already know that
Which one, ma'am?
the splitting it into two cases?
This?
Yes, if you already know that before and after 0 they don't equal each other.
Yes, but I never talked about I never talked about that point. Right? So talking about points before and the tangents there, we talked about points after and the tangents there, but we never talked about trying to make a tangent there. And that's what that last thing is supposed to be. I know it winds up being the same here. Yeah. Okay? All right. All right. Yeah, that last limit, what were we doing? We looked at that point, and then we drew secants, and then we took the limit of the secants to try to find a tangent, and flunked. Questions? Okay. All right. Here we go. Non-differentiability. How can f prime a fail to exist? When a is in the domain or close to the domain of f. Okay. Or in other words, how can we fail to find a reasonable tangent slope? Or how can we fail to find an acceptable limit of the secant slopes? So case 1. Corner or kink? Okay. I went crazy trying to phrase these properly. But I don't think you guys have to go crazy over them. Okay? If you understand them, great. Try to understand the basic idea here. Okay, corner or kink is exactly what it looks like. Okay, an abrupt change in direction. All right. We talked about the absolute value a moment ago. We talked about this in the previous class. And this is something that I put up as one of those try it if you like type graphs. Okay, and all of them are corners or kinks. Okay, the one-sided limits of the difference quotient, which we could also call the one-sided derivatives, they exist, but they disagree. Okay, so if I try to draw the tangent based on this point in the past, okay, or I do that limiting process from the left, I wind up with a tangent like that. Okay, if I do it here and the immediate future, I get a tangent like that. Both those slopes are fine, but they disagree with each other. Okay, so that's the problem here. We get an abrupt change in direction. If I had a car traveling this way, left to right, the car would have to turn at an instant, like that, and that's bad, okay? Same deal here, abrupt change in direction. Same deal here, abrupt change in direction. Okay? One other thing you can think of is that there's no way of drawing a tangent there. Okay? You can zoom in here all you want. That's never going to resolve. You're never going to straighten out to a line or anything that looks like a tangent. So not differentiable at that point. Okay? Okay. I wrote about 20 different explanations. If you want me to explain any of them, I will. A cusp. This is just an extreme corner. Again, you look at those one-sided limits there. Okay? One of them blows down, the other one blows up. Okay? So you have disagreement, but you have disagreement between infinities. Okay? And how can you see that in here? This thing approaches verticalness at the cusp. Okay? The other one just disagreed. This one's actually going straight up and down. So that's what's going on there. And again, we're non-differentiable at that point. Okay? So if again we fix a point here and we look at it and we try to build that tangent, the secants blow down in slope, and approaching from this side, the secants blow up in slope. And if you had that car that's going from left to right along here, it would have to turn 180 degrees and then keep going. Okay? 3. Vertical tangents. Some people classify that as a vertical tangent, okay? Because you'll notice that at that point, if you had to draw something to represent what that curve looks like, you'd draw a line that's going straight up and down. So let's treat it separately. Okay, vertical tangent, exactly what it sounds like. If I draw a tangent here, it's going straight up and down. If I have my car going this way, at that point, it's either pointing straight north or straight south. And the trouble is that plus infinity and minus infinity are not acceptable slopes. Okay, that's the problem here. If I try to construct the tangent using that secant limit, the slopes blow up, and coming in on this side, the slopes blow up. Okay? So if the limit fails to exist, going to infinity or minus infinity in the same way on both sides, we have this kind of thing. Again, all you really need to know is look at that thing, there's clearly a vertical tangent there. Okay? Okay? And again, the square root thing is sort of the same problem. If I tried to draw a tangent here, I would draw it straight up and down. Okay? So the square root's kind of got two problems. One is that one of the one-sided derivatives doesn't exist, and the other is that if you had to draw a tangent, it'd be vertical. Okay? Any questions about this? Final one. Any discontinuity at all. Anything, okay? Removable, whoa. Removable, jump, infinite, that oscillating thing we talked about. Any discontinuity, and you become not differentiable. Okay? I can prove this to you if you like. If f is discontinuous at a, f is not differentiable at a. Do not get this the wrong way around. Okay? It's possible for f to be not differentiable at a, but be continuous at a. Okay? Get that if-then in the right way, or just forget about it. Okay? And if that's confusing, let me know. But again, it's possible for f to fail to be differentiable at a, and yet be continuous at a. Otherwise, what were those other three examples talking about?
Wait, I don't get it. Like,
The direction?
yeah, the discontinuous, like the statement.
Okay, if you find a discontinuity of any kind, a jump, a break, an infinite thing, anything you want, any discontinuity, and it can't be differentiable. And the reason is, if you try to calculate the one-sided limits of the difference quotient, one of them at least fails to exist.
Okay.
Try it anywhere. Zoom in on something with a break in it, and you'll see that you can't draw a decent tangent.
But you said that it can also be continuous.
I said the other direction doesn't work. I said it's not true that if f is not differentiable, then f is discontinuous. That's not true. Okay? It's this way. If this, then this. Okay? The other one obviously isn't true, otherwise these three cases wouldn't be there. Okay? That might be creepy, it might be confusing, just let me know, okay? And I'll elaborate. Okay? Just think about it for a bit. Okay? That's the direction of the implication, not the other way. And again, if it's too confusing, ditch it. But if you see a discontinuity, you're not going to be differentiable. Okay, that's easy to see in the case where f at a is not defined. If f at a is not defined, the difference quotient isn't defined at all. So obviously the derivative doesn't exist. And if you have that lovely car going through a discontinuity, it has to teleport to get to keep going. And that's bad. Again, think about that. If you got questions, let me know. I'm hell-bent on finishing this today. Okay. All right, not at the risk of complete misunderstanding, obviously. Okay, here we go, just for fun. You all loved my pathological example last time. Okay, the Dirichlet function was what? It was defined everywhere, continuous nowhere. This sick, crazy thing, and you don't have to know what that top thing means. I do. The Weierstrass function. So what's the deal here? This guy's continuous everywhere. It's defined everywhere. Differentiable nowhere, or possibly almost nowhere. Okay? What happened here was you took a wiggly thing and added faster and faster wiggles on top of it. Okay? It's too bumpy. Okay? Anywhere you zoom in, so I could zoom in on any piece of this, blow it up, and it would look exactly like this thing again. It's never looking like a straight line. Too damn bumpy to have a derivative anywhere. Okay? Just for fun. So, bottom line. If you're going to shuffle, guys, do it quietly, because I think I've got 2 minutes left. Okay, bottom line. Functions are differentiable. Now let me just say something. This isn't a histology course, okay? Your job isn't to classify these things, okay? It's to recognize them. If you see one of them, there's a problem, okay? No one's going to panic over corner or cusp on a test or something, but just recognize them and be able to have in your head a picture of what each of these guys looks like. Okay, functions are differentiable where they are unbroken and smooth. Locally, or in other words, zoomed in, they look like non-vertical lines. Functions are differentiable where they are unbroken and smooth, and locally or zoomed in, they look like non-vertical lines. And you can look at any of these guys and you'll see that if you at any of these points, you've either got a break or a lack of smoothness, and if you zoom in, it won't straighten out to a line. Okay? There's a problem, and you can't draw a decent tangent. Okay? Okay. Next class, I'll talk about higher order derivatives briefly, and then we'll do differentiation rules. Is today Friday? Have a beautiful weekend, everyone. If you have any questions, come talk to me. Thank you. Point one. Last time I talked about places where a function is not differentiable. I just want to point out you don't need to know all of the things I said, okay? It's important to me that I know a lot of things and a lot of ways of interpreting things, but you don't have to know them. Okay? So for instance, I talked about the limit of the difference quotient, I talked about the limit of the secant, I talked about building a tangent, I talked about that car going along, I talked about zooming in, and I talked about roughness, okay? But you look at those cases that we talked about, and if you can understand them, you should be okay. If you want to learn more stuff, great. But don't panic if you didn't understand all 10 things that I said, all 10 versions of the explanation, okay? Okay. Okay. And just one thing, because someone said they were confused. The last case that I talked about for non-differentiable points, what I said was, if this continuous, then not differentiable. Okay? Know that, understand it. If you got any questions, let me know. That's it, that's the rule. All I was saying at the end was don't screw the rule up, okay? So if I tell you something like that, know that and not some modified version of it. Okay? Saying Taylor Swift is a woman is different from saying every woman is Taylor Swift. Okay? That was the point. Don't get things reversed, because they're wrong in reverse sometimes. Okay? Alright. Alright, any questions before we start? Okay. All right, we will finish whatever this was, 3.1 today, quickly, and then we'll move on. Higher order derivatives. Okay. The derivative of f is a function, so possibly it can be differentiated too. So, when you differentiate f, let's say with respect to x, when you differentiate f, you get f prime, or interesting stuff going on here, or df over dx. Okay, that's a function, you may be able to differentiate that too. You differentiate that. I appreciate that a lot of you know a lot of this. You get what's called the second derivative. d squared f over dx squared. Okay? Differentiate again, and you get third derivative. I will not be going on forever, I promise. d4f over dx4. 2, 2, 2, 3, 3, 4, 4, 4. And so on. Okay? So you just keep adding primes or increasing those exponents to denote those higher order derivatives. And once you get to 3 primes and above, it starts getting tedious, so you just put brackets and the number of the derivative, okay? Don't confuse this with the 4th power of f or anything else. Okay? I'm guessing we won't try to screw you up on this, but if you see brackets in an exponent, typically means that number of derivatives have been applied. Okay. Okay, and just as this was talking about the instantaneous rate of change of this is talking about the rate of change of the rate of change, and so on. So these are higher order rates of change. And for example, we have position as a function of time. The first derivative is called what?
Speed.
Thank you, velocity.
Velocity.
Speed is the absolute value. Second is called?
Acceleration.
Yay! Oh, I'm sorry. Okay. And the third?
Jerk.
Very good. Jerk. Okay? And the reason that's there is that a P with 3 primes on it looks so much like that. And the guy wearing that was a right jerk. Okay? That's 3.1. Questions?
Wait, it's like
Do we have to know the whole inscription? No.
No. Is it actually jerk?
Yeah.
Oh, okay.
I wouldn't write something on the board as just a joke. Yeah. As feeble a joke as that.
Sorry.
Yeah. And yes, I can say the whole inscription.